Hey everyone, and welcome. Today, we're going to roll up our sleeves and tackle a real cornerstone of linear algebra, Gaussian elimination. And trust me, by the end of this, you'll understand why this thing is known as a total computational beast. Let's get right into it. So picture this. You're staring at a massive grid of numbers, a matrix that could represent thousands, maybe even millions of equations. It looks pretty intimidating, doesn't it? The million-dollar question is, how do you even start to attack a problem like this to find a solution? Where's the first step?
You know, the secret to solving a lot of really complex problems isn't to go for the final answer right away. Nah, that's too hard. Instead, what we're going to do is transform this messy, complicated problem into one that's much, much simpler to solve. Our first job is just to change the matrix itself into a friendlier shape.
And this is what we're aiming for. This beautiful thing is called an upper triangular matrix. Just look at it. See how all the numbers below that main diagonal line are all zeros? Once you get a matrix looking like this, solving it becomes incredibly easy. You just solve the last equation, which is super simple, and then you work your way back up. It's a piece of cake. So think of it this way. Our whole mission here is to create this nice, clean staircase of zeros in the bottom left part of the matrix. We're going to do it systematically, column by column, just knocking out every number below the main diagonal. This visual goal, this staircase, is what's going to guide us through the entire process. So, the big question is, how do we actually make those zeros? I mean, we can't just get an eraser and wipe them out, right? We need a set of perfectly legal mathematical moves we can use to transform the matrix. Let's take a look at how it works. It's actually a beautifully simple little recipe that you just repeat over and over again. First, you pick what's called a pivot. That's the number on the diagonal in the column you're working on. Then, for every number below it that you want to get rid of, you calculate a special multiplier. So say your pivot is a 2, and the number right below it is a 6. Well, your multiplier is 3. Then you just subtract 3 times the entire pivot row from that target row. And boom, the 6 turns into a 0. You just do that little dance for every single number you need to eliminate. Okay. So we've got the how, we know the moves, but for anyone who's actually trying to solve big problems in engineering, finance, you name it, there's a much more important question. How much work is this actually going to take? This is where we have to start talking about computational cost. All right, let's break it down. To clear out that very first column in a big n by n matrix, you pretty much have to touch every other element. That's about n times n operations, or n squared. Now, when we move over to the second column, the problem is a little smaller, right? We're only focused on an n-1 by n-1 little box. So the work is roughly n-1 squared. You see the pattern? The amount of work we have to do gets a little smaller with every column we finish. So to figure out the total cost, all we have to do is add up the work for each column. And what we get is this really famous series in math, the sum of squares. Now, we could do all the math, but calculus gives us this awesome shortcut. It turns out that for any reasonably large matrix, this big sum is almost exactly n cubed divided by 3. It's a fantastic approximation. But hold on, there's one really important detail we need to think about. When we say we do one operation to change a number, what are we really doing? Well, think back to the process. First, we have to multiply the pivot row by our multiplier, and then we have to subtract it. That's 2 separate steps, a multiplication and a subtraction, for every single number we update. So we just take our n cubed over 3 formula, and we multiply it by 2 to account for both actions. And that gives us our grand finale. The total number of operations it takes to do Gaussian elimination is about 2/3 times n cubed. This simple little formula, it's one of the most important results in all of numerical computing. It tells us so much. So we have this formula, 2/3 n cubed. Big deal, right? What does that actually mean in the real world? Why is that little cubed number so incredibly important? Well, that cubic growth, it's the elephant in the matrix, and it changes everything when you start working with big problems. Let's make this super concrete. Let's say it takes your computer about 1 second to solve a system with a 1000 by 1000 matrix. Now, what happens if you just double the size to 2000 by 2000? Your first guess might be, oh, it'll take 2 seconds. But because of that n cubed rule, the time gets multiplied by 2 cubed, which is 8. It's going to take around 8 seconds. This is the key takeaway, the rule of thumb you need to remember. Doubling the size of your problem means 8 times the work.
This isn't a gentle curve upwards, it's an explosive cost. And it's the reason why going from, say, 1 million equations to 2 million isn't just twice as hard. It requires a massive leap in computer power.
And that really brings us to our final thought here. This n-cubed rule isn't some abstract thing from a math textbook. It literally defines the boundaries of what's possible in huge fields like weather forecasting, designing new materials, or training giant AI models. So the question I'll leave you with is this. Knowing this fundamental speed limit is there, how does it drive the hunt for even smarter algorithms and more powerful computers to tackle the biggest scientific challenges we face today?